Good morning, everybody. Happy Friday. We've worked on a problem with two blocks connected by a rope on a ramp before in problem number 18, I believe it was. So how about we bump up the challenge to 3 blocks this time? Plus, we'll see how the system changes when we snip one of those off. Here's what we're working with. One thing I plan on doing in the videos moving forward is to just skip reading the problem description, since I'm sure most of you know the problem already, and it helps make the videos a little shorter. If this is completely new to you, though, please feel free to pause and read through everything on this slide before proceeding. Otherwise, let's get started with part A. We'll ignore most of the picture down here and focus on block A specifically to kick off our free body diagram. I'll introduce some coordinate axes off to the side here, then also superimpose the same set directly onto block A. Our first vector is block A's weight, which will point straight down. Since block A stays on a flat surface as it moves to the right, the normal force will point upwards and have the same length as the weight vector. That's it for the y direction. Let's switch to the x. As you can see here, we have the rope attached to the right side of block A, and that will be pulling the block in that direction. So let's include a tension vector there. The tension between block A and block B may be different than the tension between block B and block C, though. So we'll label this one as T1, just to be safe. And in the minus x direction, we have the force of kinetic friction resisting the block's motion. And that's all our vectors regarding block A. Thankfully, we don't have an acceleration vector to include here due to block C descending at a constant velocity, which implies no acceleration. Since all the blocks are physically connected by taut ropes, that means that block A and block B don't have an acceleration either, for now. So that's one half of part A done. Let's move on to the other half with block B. With this block, we'll have to make some adjustments before we start labeling vectors. As you can see in the top left corner, I've adjusted the x-axis to be at the same angle as the ramp. And we are completely allowed to do this as long as we remain consistent in our directions. Moving to the right is still equivalent to moving in the positive x-axis, and similarly with the y. It's just that the block is on a ramp this time. You'll find that the vectors are pretty similar here to what we had in block A. There's still a weight vector for block B pointing straight down, and a normal vector, except now it's pointing perpendicular to the ramp. But what about in the other direction, in the x direction? Well, here we have a rope pulling on both sides of the block now, with possibly different tensions. Thus, we'll call the tension between block B and block C T2, and we'll keep the previous notation of T1 in the other direction. Let's not forget about kinetic friction either, which also points in the same direction as T1 to resist block B's motion up the ramp. Last thing to do is to break this weight vector up into components, as it doesn't lie directly along the minus y-axis. We can insert our angle here, which allows us to label the cosine and sine components of the weight in these locations, and part A is now done. Both free body diagrams are completed. Before we move on to part B, let's also create a free body diagram of block C for the sake of completion. It's incredibly easy, since this block only moves up and down. The weight will point downward, as you would expect, and since the tension pulls on the top side of the block, we'll also include an upward T2 tension vector. And that's it. On to the sum of forces analysis, starting with block A. We have our vector equation of Newton's second law up at the top, and we'll start with the sum of forces in the x direction. There's just two vectors here, the T1 tension vector and the kinetic friction vector acting on block A. Since there's no acceleration, we can slide this frictional term over to the right-hand side to make it positive, then exchange that term with its definition. We don't know what the normal force acting on block A is yet, so let's hop over to the y direction real quick and see what we can get out of that. Again, it's just, two terms, no acceleration, so the work is cut out for us. The normal force here is just equal to block A's weight. So let's grab this and go back to the sum of forces in the x direction up here and plug that in, like this. Now, we know this coefficient's value and block A's weight, so let's just go ahead and plug those in and solve for T1. Truncated to the proper number of significant figures, here's our answer to part B, 8.8 newtons. To get the weight of block C for part C, first we'll have to figure out the value of tension 2. We'll get that in this slide with a little bit of work. First, our sum of forces in the x direction acting on block B looks like this. There's a couple more terms to deal with on the left-hand side, but there's still no acceleration, so that's not too bad. We want the value here of tension 2, so let's put all these negative terms over on the right-hand side to make them positive. Next, we can substitute in the definitions of tension 1 and the kinetic frictional force acting on block B, like that. Again, we have a situation where we don't know what the normal force of block B is, so let's investigate the y direction and see if we can get that. Well, in fact, we can. Super simple stuff here. In fact, just one line of work again. The normal force is just the cosine component of block B's weight. So with that, we can snag this and move back up, plug that in here, and get a full expression for tension 2. To save myself a little bit of writing space on the screen, I'm going to factor out the weight of block B from the second and third terms here, like this. And we know what all these quantities are as well, so let's plug and chug and see what pops out. Looks like it was definitely the right move to label the tensions differently, because this one is much bigger than tension 1. Now, this value is going to play directly into the weight of block C, as we'll see next. Okay, here's our other block. The sum of forces in the x direction is, of course, 0, because this one only moves up and down. And we get a nice expression in the y direction that tells us, hey, if you move the weight of block C over, tension 2 is equal to the weight of block C. And this is that 30.8 Newton value from the previous slide. So part C is now done. Cool. In part D, we're going to snip the rope connecting blocks A and B and pretend like block A doesn't exist anymore. Does this change any of our vectors? Well, a few of them. For block B here, the weight and the normal vectors will remain the same. Okay? Changing the blocks doesn't do anything to that. The tension between block B and block C will likely change, though. In case you're wondering why, it's because block C was designed to fall at a constant velocity with two other blocks attached to it. If we snip one of those off, it's not the same setup anymore. And block C is likely going to accelerate, which means block B will too, since they're physically connected. And that will also result in a change in our tension, which we'll now label as tension 3. Again, just to be safe. We no longer have tension 1 acting in the opposite direction because we cut the rope, but we can't forget about the kinetic friction, which we'll include there. Again, the weight vector needs to be broken down, so we'll slap on an angle break the weight into components, and include an acceleration vector up the ramp. And that's it for block B. Let's check out block C next. The weight remains the same, of course, but we need to exchange the previous tension of T2 with tension 3 now, and add an acceleration vector pointing down off to the side. That's all. The last step is to do the sum of forces analysis again and solve for the new acceleration. Let's bring block B back into focus. We begin at the top like we did before with Newton's second law and the sum of forces acting in the x direction. One less term on the left-hand side compared to before, but now we have ma on the right. Do a little simplification by replacing the frictional force on block B with its definition, as you'll see here. And you can either do a sum of forces in the y direction again to get the normal force, like this, or you can grab the previous definition that we had from before, since it's still the same. Either way, doesn't matter. We will take this and plug this into our expression above, and this is as far as we can go for now. Underline this piece for the time being, and we'll come back to it in a moment. The story here with block C is identical as before, at least in the x direction. There's nothing going on there. In the y direction, here's what we have though. Let's do some algebraic manipulation to get the acceleration term on the right positive by multiplying both sides by -1, like this. There's nothing else we can do with this measly little equation either, so let's underline this one as well and prepare ourselves for a trick that we've done a couple times in the past to get an acceleration. Recall that since block B and block C are physically connected by a taut rope, they're going to share the same acceleration. This means that we can add the left-hand sides and the right-hand sides of these underlined equations to get the acceleration variable, like this. Notice that our tension 3 is going to cancel out because we have a positive term of that here and a negative term of that here. So when we get rid of that, here's what that looks like. Before we move forward, let's do ourselves a little favor and save on some work. Instead of doing some side algebra to figure out what these individual masses are, let's multiply both sides of this equation by g, like this. Now what we're going to do is absorb g into the terms on the right-hand side and then factor out the acceleration, like this. Why did we do this? Well, we know what mg is. That's just the weight, and we were given the weight of block B, and we figured out what the weight of block C is through finding out tension number 2. So why do extra work if we don't have to? I will exchange the mg terms for the weight terms in the next step, like this. And at this point, we'll divide both sides by the sum of the weights. And here we finally have an expression for the acceleration of both blocks. And when I plug in our numbers, I get the following 3 significant figures. And the problem is now complete. Let's bring everything together on the solution card and kind of review what we did here. In part A, on the 3rd and 4th slides of this video, we drew complete free body diagrams of blocks A and B. So check back on those if you need to see what that looked like. In part B, we calculated the tension between block A and block B, which we called tension 1, or T1, and that's the 8.8 Newton value that you see here. Then in block C, or excuse me, in part C, we used our sum of forces analysis to equate tension 2 to the weight of block C, and that was the 30.8 Newton value that you see here. Definitely larger than tension 1. And finally, in part D, once we snipped the rope connecting block A and block B, we found that this caused the remaining blocks to have a new shared acceleration, which is this 1.54 meter per second squared value that you see here. And that's it. Thanks for watching, everybody. Have yourselves a great weekend. Take care.